No, exactly. But it wasn't you.
Okay, if we can turn to page 15, run to and we'll work on let's do a implicit differentiation problem together. So something that we haven't yet seen, and we're going to see a lot more later this semester, and especially next semester, is what an FRQ, free response question, look like on the AP exam. Most free response questions are involving second semester content, but first semester is the foundation for second semester. So this is one of those few, or I wouldn't say, yeah, I mean, definitely majority free responses second semester content, but no, I would still say, yeah, still a few that we're going to look at first semester. And this is the first one. This is the first one that we're seeing what free response can look like. So you can see that typically free response question has 3 to 5 parts, usually 3 to 4, and every portion there's detailed partial credit that can be given, but when we work through a problem, we're not going to know exactly how they're going to be grading it, but we have sort of an idea. Every free response question is going to be graded out of 9 points. But typically, if we can just, on the AP exam side of things, if we can score anywhere between, 4 to 5 points per FRQ, that's really good. And anything more than that is bonus. So, but we're going to do a lot more free response questions second semester, and when we do AP exam review, we have a month and a half just to kind of cycle through as many FRQs as we can. So it says, consider the curve given by xy squared minus x cubed y equals 6. Show that the derivative is equal to this. So this is not the starting point of our problem. This is the ending point. So I see some students try to start from this equation and go through the process, but we're not going to even look at this. This is going to be, they're basically telling us what the answer is. We just have to show the work that connects between the two. So basically, we're not even going to look at the dy dx. We're going to look at this. We're going to look at the starting equation and try to figure out how can we get from this equation to the derivative. So make sure that we're looking at the starting equation and not looking at the dy dx, because that is not the starting point of our problem. Okay, xy squared minus x cubed y equals 6. What processes are involved? as you look at this equation, if we want to find the derivative. What do you notice? And do you see a need for implicit differentiation? That's right. We see y's mixed into the equation. Usually y's are not in these spots. Usually it's y equals and everything else in terms of x. So we know there's definitely implicit. Okay, what else? What does the xy squared indicate we have to involve as well? Product rule. How many times? Twice. Yeah, xy squared. This is one place where product rule needs to be applied because x times y squared, these are being multiplied. And then x cubed y, this is also another instance when two different variables are being multiplied. We got to go through product rule again. So we got to go through it twice. Okay. And then there's, yeah, so I'll write that down. Product rule twice. And then as we do that, there's one thing we have to be careful of. What do we have to actively be aware of? Otherwise, we may get caught with a slightly wrong answer. Do you see any potential trouble spots as we go through those processes?
The negative.
The negative, yeah. The negative has to do what eventually after the product rule gets applied? It's got to be distributed, yeah. So, okay, so I'm going to write the equation down and we're going to start working it. I'm going to leave that x cubed y in its own set of parentheses as a reminder that as I build out my product rule, I also want to keep those parentheses as a reminder about that negative in front. Okay, f prime g plus f g prime. We'll do that twice. Okay, so I have everything set up here. So let's see if we can go through identifying whether to pull the derivative or the expression and when the dy dx shows up. Okay, so remember dy dx only shows up if we're asking for the derivative of a y variable. Okay? If it's not asking for, well, first off, if y doesn't show up, then there's no dy dx. And also, if it's not asking for y's derivative, then dy dx also doesn't show up. Okay. All right, try that. And I'll work through it at the same time that you guys do. Right, what does 6 turn into? 0. Yeah. Okay, so right here, this is the most important step of the part A, because this is where the derivative is applied. Any questions up to this point? Okay, so from here, there's just combining, cleaning up, adding, subtracting, collecting your dy dx terms, and now the rest is just algebraic. There's no, so the calculus was just from here to here to here, and the rest is just cleanup. And we know what we're after. After everything is cleaned up, our answer should look like this. So this is nice that this problem tells you what the answer is. We just have to make the connection between the starting and the end. Let's see if we can get it to match this answer here. All right, so here's my dy dx. This is my derivative function. Sorry, derivative equation. Any full order pair I give it, in return, it'll give me a number, and that number will tell me how steep this original curve is at that point. And we double check, it does match up. Now, if you had collected your dy dx's on the right side, it wouldn't have been wrong, but your dy dx would have ended up with all the signs being opposite. It may end up like being negative 3x squared y plus y squared all over negative 2xy plus x cubed. And to make this look like this, you can just multiply your numerator and denominator, distribute with -1, and this should match with this equation. So collecting your dy dx terms on the left side may not necessarily guarantee that your answer looks like whatever answer College Board has, but just know that you can always convert your version to their version by multiplying by -1 top and bottom if yours is off by -1. Okay, any questions? Okay, part B. It says find all the points on the curve whose x coordinate is 1 and write an equation for the tangent line at each of these points. Now, we talked about how the unique thing about these equations is that more likely than not, they're not going to pass a vertical line test, which means that, if a graph, looks like this, for instance, you may have overlapping x values, right? One x value is here, one x value is here. There's two different places that share the same x value. This will never happen on a function, but on an equation where it doesn't pass a vertical line test, that's fine. And here it's asking for, find all the points. So potentially having two different points or more than 2 points, 2 or more points. And then after we find those ordered pairs, we'll find the slopes at these points and then we'll write the equations of these tangent lines. I mean, these may not be what the graph looks like, but I just want to point out this is our goal. Our goal is that there's multiple points. We got to find both those points and then find the slopes and find the equations of tangent lines. All right, so how do we find the points where the x coordinate is 1? What can we use to find location of a graph? We have the equation available. We have the derivative available. Which one do we use if we're trying to locate the point? Function, yeah. Well, I'm going to call this original equation. It's not quite a function, but yes, we're using the original equation. So we'll plug 1 in for x and then see what the y gives us. Okay, so part B. And we're open to the possibility that there may be more than one y value, because we may have overlapping x values. Okay, so replace every x with 1. Okay, 3 separate terms here. What do we do from here? What would you do next? Can I do this? And say y equals 6 and y minus 1 equals 6. Can I do that?
Yeah.
We can't. We can't. Why is that? I know it's tempting. That's why I want to point that out to you so that you're aware of these issues that students experience. I know this feels like it makes sense, but this only works when this number is what? 0, right? And we can't do it any other way. It feels like an easier way to factor, but we can't factor this way. So this is not going to work. What should we do then if we're at this stage? Yeah, we gotta do trinomial factoring. I know we prefer not to do trinomial factoring, but we just, now if it was y squared minus y equals 0, then great. You can factor the y out, but we can't have that 6 sitting there, and we're not going to get the right answer if we do it that way. Okay. All right, so multiplies to be -6, adds up to be -1. -3 and +2. So what does that tell us then? What are the ordered pairs where we're interested in? Two different y values, right? So what are our order pairs? Okay. How many order pairs do we have? 2, yeah. We have 1, 3, and we have 1, -2. Okay, so it's kind of like this. We have 2 different points on the graph that share the same x value, but they're in different locations. So now it says, write an equation for the tangent line at these points. So let's focus on 1, 3 first. How can I find the slope at 1, 3? Derivative, yeah, your derivative will tell you your slope. So the way that notation that we use to indicate if we want to put a full order pair into the derivative it's going to be dy dx with a vertical bar 1, 3 to indicate that it's not just, y prime of 1, it's kind of y prime of 1, 3. And the notation for that is this dy dx 1, 3. Okay, so every x gets replaced with 1, every y gets replaced with 3. And we're just inserting into the derivative to get our slope at that point. And we'll do it again for the other point, and then we should have two separate equations. Next up, at 1, -2, we'll take this location, put it into the derivative, get our slope, and then do point slope form. My second order pair, 1, -2, my slope is a positive 2. Okay, any questions with part B? Part C, I just want to talk through it. The algebraic steps is a little messy, but maybe we can come back to this after we try other variations of this problem. So part C is saying, find the x-coordinate of each point on the curve where the tangent is vertical. Tangent is vertical. So we're going to have to be able to know how to find where the tangent is vertical and also where the tangent is horizontal. Do you guys remember, where do we look if we're trying to find a vertical tangent? Denominator of the derivative, right? So yeah, so denominator of the derivative will tell you where the vertical tangent is, and vertical tangent is where the slope is undefined. Right? What if we're looking for a horizontal tangent? Horizontal tangent is where the slope is 0. We set the what? We look at the numerator. Okay, so we're gonna do more of those types of problems probably tomorrow. I want to focus our attention on that. But vertical tangent is set the denominator equal to 0. Horizontal tangent is set the numerator of the derivative equal to 0. Okay. So the algebra is a little bit messy with that, but maybe we can do the easier or the more straightforward problems tomorrow, and we can come back to part C later on. But our starting step is this. We set the denominator of derivative equal to 0. That's our strategy to find those locations. Okay. Another important variation that we want to be able to know how to do, especially knowing what AP exams can potentially look like. We're going to look at product rule, quotient rule, and chain rule in terms of their function notation and be able to interpret using a graph. So if you can turn to page 19. So now we're just reviewing. We're just going back and looking at all these different variations of a power rule, product rule, quotient, chain. Okay. Page 19. So it says in exercise 8182, use graphs of f and g, let p of x equals f times g, and let q of x equal f divided by g. So part A says find p prime of 1. So before we can find p prime of 1, we first have to find p prime of x. And if I want to find p prime of x, I have to look at how p of x is set up. If I want a derivative that has f of x equals f times g, guess what we have to do to find its derivative? Product rule, right? So product rule f prime g plus fg prime. Let's just fill that out. Sorry, f, not p. Now that you have your derivative spelled out, now I can involve plug in 1. All right, so g of 1 and f of 1 is just pulling the y values of the graph at their corresponding points. What do you think we're looking for on the graph if we're asking for f prime of 1 and g prime of 1? Good, slope. So this is a good way of connecting or reinforcing the idea that derivative is just a fancy word for slope, right? And normally, if it was a curve, we wouldn't be able to know what the slope was, but because these are nice straight lines, we know we're going to be able to know exactly what the slope is at a point, right? Because we're going to have nice consistent slopes within each line segment. Okay, so to find slope, we can just do rise over run, pick 2 points that land nicely at coordinate points, and then just do vertical over horizontal, and then that will tell us the steepness of that line. So f prime of 1. I'm going to go to 1 on f graph, which is here. If I just pick another point on this line and just do rise over run, what's the slope of this line segment? Just what? What's the steepness of this line? Yep, up 1 over 1, right? Up 1 over 1, steepness is 1. So replace f prime of 1 with 1 because we found the slope of the f graph at 1. Okay, g of 1. G of 1. Now we're asking for the what of the g graph? Is this slope or is it what? Or you tell me, what do you think g of 1 is? Which is? What's the y value there? 4, okay. All right, f of 1. Back to this same point, but now instead of asking for the slope, we're asking for the y value. Y value is what? 6, right? Okay. All right, g prime of 1. Or what are we looking for now on this line segment? Slope, okay. What's the slope of this line segment? What you guys get? Rise over run. Down 1 over 2, so -1/2, right? Okay, they're very comfortable with seeing what information we need to pull from the graph. Sometimes it's order pair, sometimes it's slope, and the notation tells you whether it's slope or order pair. All right, so this gives us 4. 4 times 1 is 4. 6 times -1/2 is -3, -3. 4 minus 3 is 1, so that's our answer. That is our P prime of 1. So if it's a diagonal line, we know it's rise over run. Let me just point out some exceptions here. What if it's a horizontal line? My slope would be what? 0. What if it's a sharp turn? My slope would be what? Not 0. What's the slope at a sharp turn or at a corner? Right, if it's a nice smooth curve like this, then yes, my slope will be 0, right? But what's the slope at these corners? We're going to say what? Anyone know?
Doesn't exist.
Doesn't exist. Yeah, slope does not exist at a sharp turn. So if there's a corner, if it's not a smooth transition, because here the slope is all of a sudden changing from negative to a positive, and there's no transition. It's not going to, and there'd be a slope 0. So to remember that any corner points, any sharp corners, any sharp turns, it's always going to give you slope undefined. And if slope is undefined, if it shows up anywhere in your derivative, then it's going to wipe out that whole value, and it's going to make everything undefined. Okay, we can't cancel out undefined, for instance. So if one part is undefined, it's going to impact the whole thing breaks down. Okay, Q prime of 4 is part B. Right, if I want to find Q prime of 4, I first have to find Q prime of X. To find Q prime of X, we got to find the derivative of Q of X. And what rule do we have to involve if we want to find the derivative if I have 2 terms divided by each other? Quotient rule. Okay, so let's build out quotient rule. F prime G minus FG prime all over G squared. Then replace every X with 4, and then go to your graph and replace all those function notations with either the slope value or the Y value at 4. Okay, try that. I also have the key attached on page 21, so you guys can check your work, but I can also go over it once you guys have a chance to try it. Okay, so here's my derivative, f prime times g minus fg prime all over g squared. After we have our derivative spelled out, replace every x with 4. And then I went ahead and I highlighted 4 on both the f and the g. And it's either asking for the slope of the f graph at 4 or the y value of the f graph at 4. If it's on the g function, it's either asking for the y value of the g graph at 4 or the slope of the g graph at 4. So the slope of this f graph at 4, it's part of a slope that looks like -1. So I can go down 1 over 1. It's the same slope all the way through. And then the slope of the g graph at 4 is a horizontal line. So that horizontal line indicates a slope 0. And then we find the y values of the f and g. And then we just clean it up. We get -3 over 9, which is -1/3. Okay, so you'll see a problem like this on the test. We'll do more practice, but as of now, I guess we're okay with those steps. What's a little bit more challenging is our problems that involve chain rule. So let's see if we can go through a couple of those, and then we can put things together over the next few days. So if you guys can turn to page 23. I'm sorry, page 20, my bad, 20. I was looking at the key. Page 20. So one potential mix-up that students experience with chain rule is sometimes students look at this and so this is a composite function. You got a function within a function, f of g of x. S is defined as g of f of x. So we have to understand these are composite functions, got a function within a function. But sometimes we mistake these for product rule. So I want to point out what the difference is between product rule is. So product rule would be if it was like f of x times g of x. You see something that makes it easy to identify whether something is product rule versus chain rule? You think there's an easy difference that we can tell between the product rule and chain rule? So yeah, parentheses. Also, the number of x's. If you see two different x's, that means they're part of two different expressions. If they're part of two different expressions, then it's going to be either product rule or if we're divided, it's quotient rule. But if it's f of g of x, you have a function within a function. So if there's only one x, then we should be able to know, even though there's f and g involved, this is chain rule and not product rule. So I want to make sure that we can look at something in function notation and be able to tell, okay, that's product rule and versus this is something that will require quotient. Chain rule. Okay, so here's what our derivative for chain rule looked like when we were first introduced to it. It says if I want to find the derivative of f of g of x, I'm going to take the outside derivative, which is f prime, keep the inside intact, and then multiply by the inner portion's derivative, so times g prime. So to make sure we can memorize this formula for chain rule. It may not always be f on the outside. It may be flip-flop, and it really depends on what is given to you. In this case, for h, we know f is the outside, g is the inside, but for s of x, g is the outside and f is the inside. We'll have to make that adjustment accordingly. But let's do h prime first, since that's what it's asking for part A. So before I can find h prime of 1, I first have to build h prime of x. So since h is defined as f of g of x, it's going to look exactly like the rule that we learned. Okay. Next up, replace every x with what? 1. Okay, the reason why this is a little bit more difficult than product rule is because we have to kind of take things one at a time. This f prime of g of 1 is too much to do in one step. So we're going to do it one step at a time. Within this first expression, what do you think would be the easiest thing to find first? What's a relatively easy thing that we can just get out of the way? G of what? G of 1, right? That is not the full thing that we need, but it will help us move closer towards what we want to get to. We're eventually trying to get all of our function notations into something that is numeric, that is out of that notation. So let's find that piece first. Okay, so what's G of 1 equal to? What do you see? G of 1 equals to what? 4. Okay. So once we find G of 1 equals 4, you're going to rewrite this entire expression, but you're just going to replace that piece. Okay. So just keep reminding yourself that this is a multi-step process. There's more things that we need to find, but we found the first piece of the puzzle, which you said G of 1 is equal to 4. So now, once we make that initial substitution, it should feel a little bit easier, or at least more straightforward. Did everybody see that? I just replaced that G of 1 with 4. I still haven't figured out this whole piece yet, but I'm getting closer. Okay. This should now become a little bit easier to interpret, right? Now we can just look at this and say, okay, it's asking for my f prime of 4. Now I'm asking for the f graph, the slope of the f graph at 4. What is the slope going to be here at 4? -1. So now I can replace this whole first piece with -1, but it did take 2 steps for me to get from this all the way down to this, right? This was multi-step process to resolve this function within this derivative. Okay, so now the remaining piece is times g prime of 1. So what's the slope of the g graph at 1? -1/2. Yeah. Okay. Our final problem here. Let's do part B. Part B is asking for s prime of 5, but if you look, s is defined as g of f of x. So we know that we only see one x. There's definitely a function within a function. See if you can build out your derivative using chain rule. But now, instead of f being the outer, f is now the inside, right? And g is the outside. So you have to build your derivative with that in mind. And then once you build your derivative, replace the x with 5, and then piece by piece, see if we're able to get it down to an answer. Okay. All right, so go ahead and work on that, and I'll work on it at the same time that you guys do. G prime of 6. Slope of the G graph at 6. What can we say there? Slope is what? Does not exist, right? So it's undefined, doesn't exist. So if something is undefined, then it doesn't matter what the other piece is. It's also going to wipe out. Well, f prime of 5 would have been negative. It is -1, but it doesn't matter. Anything times undefined is still undefined. So undefined or doesn't exist. So if any parts of your derivative breaks down, then the whole thing breaks down. Okay, your homework is just to practice these problems here. So you're going to do page 19 and 20. Whatever, yeah, so you're just practicing chain rule and product rule. And the key is on the next page, so it shouldn't take that long for you to get through. I'll send out a reminder this afternoon. All right, go get your phones.
You're gonna have homework.
Okay.
That I know you for the last 2 days.
Great, great.
Yeah.
Thank you.
Thanks, yeah.
Clear material. It's hard, but this is hard. It's just in. Like, yes.